Look at the immense, high-voltage transmission towers that supply an entire city. Now compare that raw power to the tiny trickle of energy needed to charge your smartphone. The scale and purpose are entirely different, yet both systems operate on the exact same physical principle. We are looking at a controlled stream of electrons moving through a conductive material. Every application in electrical engineering falls into two categories based on a single variable of this flow. That variable is how the direction and the magnitude of the current behave over a period of time. Based on that behavior, the current is classified as either direct current or alternating current. These represent the foundational concepts required for an electrician, commonly referred to as DC and AC. Connecting a device designed for one type of current to a source supplying the other will result in a catastrophic failure of the equipment. To safely diagnose and wire any system, you must first build an accurate mental model of these two invisible behaviors. We begin the physical breakdown with direct current, or DC. Direct current is defined as an electrical current that flows exclusively in one single direction. This split-screen model illustrates the mechanics. Below, in the wire cross-section, electrons move in a strict one-way path. Above, a graph plots current over time. Because this pressure is constant, mapping the flow yields a perfectly flat, solid line. The magnitude, the actual strength of the flow, does not change or fluctuate in a pure DC system. This highly stable, predictable flow is exactly what delicate electronic systems require to process information safely. Everyday sources that generate this flatline current include localized storage devices like batteries, standard dry cells, and power banks. Modern solid-state technology also outputs DC inherently, independent of chemical reactions. For example, a standalone solar panel converting sunlight into electricity naturally outputs direct current. While DC's unwavering direction is ideal for stored and electronic power, pushing a constant flow over hundreds of miles is highly inefficient. That inefficiency is why the large-scale grid relies on a different method of transmission. This brings us to a more dynamic system, alternating current. AC is a current where both the direction and the magnitude are continuously changing over time. Returning to the wire model, we observe a different behavior. Electrons rhythmically push forward, stop, and pull backward. Plotted on the graph, this action traces a smooth sine wave, oscillating evenly above and below the zero baseline. Unlike the flat line of DC, the magnitude of AC is never constant. It is always rising to a peak, falling back to zero, or reversing its direction entirely. The primary generator of this oscillating wave is the national power grid. Because the grid generates AC for efficient transmission, it is the standard electrical supply waiting behind the meters and outlets in our homes and factories. Any standard appliance plugged into a wall is engineered specifically to accept this continuously reversing flow. Because AC pushes and pulls in a continuous cycle, it introduces a critical dimension of time that DC lacks, the speed of the alternation. To work with AC practically, we must measure exactly how fast it changes direction. This chart shows the continuous AC wave, but if we isolate just a single sequence, starting at zero, peaking, dipping to the trough, and returning to zero, we have what is called one complete cycle. The formal technical term for the speed of this wave is frequency. Frequency is defined as the total number of these complete cycles that occur in exactly 1 second. We measure this rate using a standard unit called the Hertz. This frequency is strictly regulated on a national level to ensure equipment operates safely and reliably across the grid. The strict standard for the Indian domestic AC supply is 50 Hertz. This means the current flowing through an Indian home completes 50 full cycles, pushing and pulling, every single second. By contrast, because DC never cycles and remains a flat line indefinitely, its frequency is 0 Hertz. The metric of Hertz creates a permanent, measurable mathematical boundary between battery systems and the grid. We can synthesize these two systems into a rigid comparative matrix for field reference. For direction, AC continuously alters its path, while DC remains strictly one way. For sources, AC flows primarily from the national power grid, while DC is drawn from localized batteries, cells, and solar panels. And for the final metric, standard Indian AC operates at a dynamic 50 Hertz, while DC sits completely static at 0 Hertz. This behavior provides a simple rule of thumb. AC means the direction alternates, and DC means the direction is direct. If you were asked in a technical interview to name a DC source, answer battery. If asked for the standard AC frequency in India, answer 50 Hertz. On real-world industrial sites, electricians rely on these definitions to read control panels and safely route power. Now that we completely understand the fundamental nature of the current, the very next step is safely connecting loads. In the next module, we will explore series circuits, analyzing how voltage and current behave when forced through a chain of resistance. Whether working on a local solar cell or routing a massive city grid, an electrician's true power is accurately visualizing this invisible flow.